Welcome to the deep dive. Today we're tackling a subject that, well, it absolutely defines patient safety, but it rarely gets the spotlight. We're talking about the post-procedure protocol in the endoscopy suite.
The cleanup.
Exactly. Our mission is to explore that meticulous, essential process of aseptic disposal. It's this whole unsung logistical choreography that kicks off the second the patient leaves the room.
And this deep dive is really, for you, the person who gets a procedure's success isn't just about what happens during the case.
Right, it's about what happens after.
It's everything that happens after.
Right.
I mean, if we talk about infection control, the battle is so often won or lost right there in the strict adherence to these disposal protocols.
Yeah.
We're going to go beyond just a simple checklist and really understand the engineering of cleanliness.
The engineering of cleanliness, I like that.
Yeah, why certain things have to be handled in very specific ways to, completely zero out those transmission risks for the staff and, of course, for the next patient.
Okay, let's unpack this. So we have to start right at that moment. The scope is out, procedure's officially done. The room is, well, it's potentially contaminated.
Potentially, yes.
So before we even get to the instruments, the first thing has to be the staff's own protection.
Absolutely. It starts with them. It starts with their personal protective equipment, their PPE. And taking it off isn't just a casual step.
It's not just ripping it off and throwing it in a bin.
No, it's a planned sequence.
Yeah.
You have to do it in order to prevent transferring any contamination from the gown or gloves onto your own skin or scrubs. And this sequence is required immediately for every single person on the team.
And right away, that distinction between contaminated waste and clean waste starts even with their own protective gear.
Exactly. You've got two different paths, and it depends on the gown. If your team member was wearing a reusable gown, that goes into a very specific marked laundry bin for, high heat medical washing.
Okay. But what if it's single use?
Well, if it was a single-use disposable gown, that's when we have to do an immediate contamination assessment.
So, if the gown was just worn, but it looks clean, no splatter, no obvious fluid contact, it can sometimes bypass that high-risk stream.
Precisely. If the gown's integrity is intact and it's not carrying visible biohazardous material, it can often go into the general waste.
But the second you see something,
The moment there is visible contamination, any splatter, soaking, any fluid contact, it has to be treated as a biohazard.
yeah,
It goes straight into the designated red bag or a biohazard container. That distinction is really the core of risk management in that environment.
that makes sense. And that contamination distinction is so crucial because it helps you separate the real danger from, say, the clean packaging that the devices came in,
Yeah.
like the sterile wrappers for the injection needles or the biopsy forceps. Those never actually touched the patient.
Correct. The packaging itself, the paper, the little plastic tray, it never made contact with the patient's internal anatomy. It's clean. It's just general waste. So the staff members should get rid of that clean packaging before they even handle the contaminated device.
To avoid cross-contamination.
You want to avoid cross-contaminating the general trash can.
Exactly. But the device itself, the actual instrument, that follows a totally different rule than its wrapper. It seems simple, but there's one factor that just instantly labels it as a high-risk biohazard, no matter how clean it might look.
What's fascinating here is the moment the device gets used, the rule is just. It's absolute. Any device that was deployed during the procedure, so anything that went down the biopsy channel of the scope,
Like forceps or a needle?
forceps, injection needle, anything, it is automatically 100% of the time considered contaminated. It is a biohazard.
Even if it looks spotless when it comes out.
Doesn't matter. It has been in the internal pathway. It has to go directly into the designated biohazard container. There's no exception to that rule based on just looking at it.
That makes perfect sense. The second it breaches that internal channel, you just assume high risk. But now we have to talk about the instruments that pose the highest immediate physical risk to the staff.
Sharps. The sharp instruments, so injection needles, electrosurgical knives, any kind of blade, they pose the single greatest threat of injury and subsequent infection exposure to the healthcare workers in that room. The protocol for handling them is all about mitigating that physical transfer risk.
Here's where it gets really interesting. Because the safety protocol for sharps disposal isn't just about the bin. It actually starts with the logistical setup of the room itself.
Oh, absolutely.
You can't have someone walking across the entire procedure room, maybe dodging equipment, while they're carrying a contaminated needle.
That's the cardinal rule, proximity. You have to set up the sharps container as close as possible to where it's being used, so often right next to the procedure bed.
And what if it's a big room?
If you have a large suite, or if the procedure means you're using items in different spots, then it's mandatory to have multiple sharps containers, maybe one at either end of the room. The goal is it's to reduce the travel distance with a high-risk item down to zero. That little walk across the floor, it just multiplies the risk exponentially.
So, okay, the staff member gets to the container. The protocol then demands three absolutely essential safety checks every single time. The first one is about the container itself.
You must check the fill level before you even get to the opening.
How full is too full?
Well, usually the containers have a visual maximum line that's often marked at about 2/3 or maybe 3/4 full. The critical thing to understand is that the slot, the opening, must be completely free. If sharps are piled up too close to it, just trying to put a new one in means you have to use force.
Yeah.
You have to push.
And that's a recipe for injury.
That is a major precursor to injury. You're physically forcing a new sharp into a crowded, dangerous space.
Okay, so the volume check is clear. Then the actual act of disposal, there's a specific technique for that too, right? You don't just chuck it in.
Absolutely not. You have to be deliberate. The sharp must be dropped horizontally into the slit of the container.
Horizontally. Why?
We want a clean, simple entry. If you drop it vertically, you increase the chance of a rebound. Some people call it the trampoline effect.
Trampoline.
If the container already has stuff in it, dropping a needle straight down onto that pile can cause it to spring back out or get stuck at a dangerous angle right near the opening. Dropping it horizontally ensures it slides safely away.
And that leads to the third check, which is making sure that horizontal slide actually worked. You need to confirm that the shuck is dropped to the bottom and it's gone from view. Why is that visual check so important?
Because if it gets hung up, in the plastic lid or the throat of the container, it becomes an invisible tripwire for the next person.
Oh, wow.
They come up to the container, assuming it's clear, and they accidentally run their hand or another sharp into that one that's hanging there. That hanging sharp has compromised the container's entire purpose, which is safe, irreversible containment. It has to be confirmed clear every time.
And this brings us to the absolute prohibition, the big safety warning that everyone needs to know, especially if a sharp does get stuck.
You should never, ever, under any circumstance, put your fingers into the sharps container to try and push it down or dislodge it. Never. That action is it's a voluntary breach of safety. It's a recipe for a very serious injury and infection exposure. If the sharp doesn't drop cleanly, that container is now compromised. You seal it, you get rid of it, and you get a new one. The time you might save is never worth that risk.
So we've covered the individual risks, staff protection, and the really high-risk instruments. Now let's shift to all the accessories and tubing that manage the bulk materials. If you look at the pumps, the bottles, fluid management, timing seems to be the next critical factor.
If we connect this to the bigger picture, the timing of disposal is a huge pillar of infection control, and it's specifically dictated by the contact risk. We basically categorize items based on how closely they were involved in the high-flow aerosolization and suction path of the procedure.
And that determines how quickly they have to be replaced.
Exactly.
Okay, let's start with the items that have to be disposed of and replaced after every single case. This list is for the highest contact, most acute risk components.
That's right. The items disposed of after every single case are the critical pathway components. And there are 4 of them.
4.
The suction canister, the suction tubing, the auxiliary water jet connector, and the air-water connecting tube. All 4 of those get thrown out immediately after one case is done, and a brand new sterile set has to be ready for the next one.
Why those 4 specifically? What's the core reason they can't wait?
They're non-negotiable because they have the highest potential for a gross microbial load and cross-patient contamination. The suction system is literally pulling highly concentrated biological material out of the patient.
Right.
And the air and water components, especially that auxiliary water jet connector, they're constantly passing fluid into the patient's anatomy or creating mist inside the scope channel. The risk of contamination sticking to their surfaces is just way too high for any kind of reuse, even for a short time between patients.
That sounds like a heavy but completely essential logistical lift. Now, on the flip side, we have items that can be disposed of only at the end of the day. This has to be a different, lower risk profile.
Exactly. This category is really about a calculated management of resources and time. These items are still necessary for the procedure, but their fluid path is kind of upstream from the main contact zone.
They're holding the clean stuff.
They're holding clean water or air that gets pumped down the scope, but they aren't actively receiving biohazard material back into them like the suction canister is.
So we're talking about the water supply items.
Correct. The end-of-day disposal items, they include the water jug or container for the auxiliary water jet and its tubing, the air water bottle, and the water bottle for the air water lens cleaner and its tubing.
And the risk here is different.
The risk here is not an acute patient-to-patient transfer. It's more about microbial colonization over a long period. By replacing them daily, we mitigate that long-term colonization risk, but we also allow the room turnover to be faster between cases. It's a strategic balance.
That makes a lot of sense. The categorization really structures the whole process, distinguishing that acute cross-contamination risk from the longer-term colonization risk. But there's one major hazard left.
The liquid waste.
The bulk liquid waste in that suction canister we just talked about, I mean, that thing contains a lot of liquid material, and if that spills, it is a serious high-volume biohazard.
And handling that liquid requires a specific multi-step chemical conversion process before it can be finally disposed of. We have to completely eliminate the liquid state.
So you're basically removing the risk of it spilling during transport.
That's the whole point.
This sounds like some practical chemistry happening right there in the procedure room. What kind of chemical are we talking about here? How does this conversion work?
It requires adding a highly effective solidifying agent. It's usually a chemical powder or a gel that's based on superabsorbent polymers.
Super absorbent, okay.
Yeah, and sometimes it's mixed with a disinfectant component.
Right.
The team member will pour or scoop a measured amount of this chemical directly into the liquid waste inside the canister right after the suction tubing's been disconnected.
Wait, you said a measured amount. That sounds like a key variable and a potential risk point.
It is.
If you don't add enough of the chemical, the liquid won't fully solidify, and then you could have a leak later on.
That is precisely the most common failure point, especially in high-volume settings. If the chemical is underdosed, you just end up with this sort of semi-gelatinous sludge. It can still slosh around, it can leak, it can shift. It's still a high spillage risk. The protocol requires ensuring the entire volume is converted into a stable, immobile solid.
Before the lid is sealed.
Before the lid is sealed. That transition from liquid to solid state is the non-negotiable safeguard.
So you start with a mobile, highly infectious liquid biohazard, you add a measured dose of a chemical polymer, and now you have a solidified, stable product inside its original canister. What happens then?
Once that conversion is confirmed, the sealed canister, which is now holding solid medical waste, can be safely processed. The whole solidified mass is just treated like any other solid medical waste. At that point, the entire sealed unit gets placed into the designated large biohazard container for final transport.
You've turned a highly mobile, high-risk agent into something stable and contained.
You've dramatically reduced the danger level.
Yes. So what does this all mean? We've walked through the entire sequence, from personal protection to sharps disposal, through the strategic timing for tubing, and finally, chemically converting liquid hazards. What we've really explored is the hierarchy of risk in the endoscopy suite.
It's a perfect illustration of how patient safety really relies on systems thinking.
Right.
Knowing exactly how to dispose of all these different instruments, accessories, tubes, and containers, knowing how often to dispose of them, and knowing the precise precautions you need to prevent infection transmission at every single stage of that cleanup.
And this raises an important question. When you think about the sheer scale of this, thousands of procedures happening daily, rapid room turnovers, and this constant need to purchase, store, and correctly dose these very specialized chemicals just to solidify liquid hazards, what are the unseen logistical and environmental challenges in scaling this? It's a continuous challenge, right, of meeting that high volume of procedures with absolute precision and chemical rigor.
It really is.
Yeah.
And it reminds us that the fight against infection isn't always about the fancy technology inside the body. So much of it is about the meticulous logistics of the cleanup outside of it.
Thank you for taking us through this essential deep dive.